Today I'm going to discuss the topic of structure padding. The structure AA here, whose member fields are N and elements from initial inspection, has a size of 9 bytes, simply because integer is 4 bytes, the first member field N, and the second member field elements is 5 because struct A, consisting of field 1, is the size of 1. Struct A has only one field, which is field 1, and the size of struct A is basically 1. Yes, it's a structure, but the size is 1. So the total size of structure AA is the size of this member field, which is 9 from initial inspection. Actually, the size of AA when in actual execution is greater than 9. The reason for this is in the design of C or in the design of a language that is communicating to a CPU or hardware. And by the way, this is also true for Rust. Okay, padding is a reality that happens in C, C++ as well as in Rust. So I think the clear description is here is any language that claims to talk to the CPU or to the hardware needs to have this feature. Why? Because by aligning addresses of variables can improve speed of execution. We must give what the hardware needs to optimize itself. And one of that is address alignment. Therefore, there are paths that's going to be inserted between fields N and elements to align the addresses of these fields. So let us try to run now. We can see here that the size of G is 12. It's not 9. The additional bytes is because of the coding that exists inside the structure. Now, if we go and watch the variable G in view it in memory viewer, here, I memset the entire region of memory G to FF for so we can see it where the region lies. So it lies in the red FF that we just were seeing here. And that is why I did a memset for this reason. For, for we can visually see the extent of G. And then we invoke access of 5, and we are going to set the element to a value. The fifth element. Well, the array elements is only valid with an index of 0 to 4. So certainly the fifth element is an out of bound access. The question here is where is 69 going to land within the memory region that I highlighted here? Because this is the memory region of G. So I'm going to press F10 now and watch carefully where 69 is going to be written in the memory. And look and behold, 69 got written into the padding area. Okay? Because struct AA have pads within them. So the value of 69 got written into those padding areas. We can see it very clearly here. It's written inside G. So I'll stop the program now. It is for this reason that if I statically analyze this code using PowerSoft static analysis, so let's do that now. Flow analysis standard. Trying to access the fifth element looks like an out of bounds, but PowerSoft is not reporting an out of bounds violation here. Why? Something wrong with the PowerSoft tool? The elements is only five uh, members, but we are writing to a cell that does not exist within because only 0 to 4 is the valid index. PowerSoft understood that this type of, I mean, it does not just examine the code as it is, but it examines the abstract syntax tree of this code when it's during analysis. So it's a deeper type of inspection. So let us try to use in this second scenario to force struct AA to not use padding. We can do that using the pragma directive. Now that we put the pragma directive here, the structure AA is not going to be padded. And the size of structure AA is definitely going to be 9 this time. There are no more paddings. The side effect of this is without paddings, the CPU is going to need more time to execute the program because the addresses of the fields are no longer aligned. But still, the CPU will run it, it will not complain. And hence, it is here we can see the reason why padding exists. It is for the CPU to execute the program in an optimized way. But we can opt to not use padding, and it will slow down the CPU. So let us try to run again this time. This time, we see that the size of the structure is indeed 9, so there are no more pads. Just like before, let us view the memory region. And then set it to FF for clarity. So this is the region marked as FF in red below. Now, we are going to write into the out of bound uh, region of the array, which is just like before, we write 69. Look carefully where 69 is going to land in the memory viewer. I'm going to put my mouse here so that it will be served as a reference. And look, the byte 69 got written outside of the region. Now that it is outside of the region, after putting pragma directive to not pack the structure, there are no more pads, there are no extra holes in the structure. If I run again Parsoft static analysis, this time it analyzes the abstract syntax tree representation of the code in static analysis, and it correctly detected the out of bound access. You can right click to this violation and you will be presented with a description of what this violation is all about. And that is all I'm trying to discuss today for this session. The key points here is, unlike open source static analyzers, which scans the code at the surface level, the Parsoft static analysis scans the code at a much deeper level in the way that C and the nuances of C behaves. That is all. Thank you.